Today we're going to have a very special speaker, Philip Wadler from the University of Edinburgh. He's a very distinguished speaker, known, Josh is telling me to speak up more loudly, so I will. He's known worldwide for his work on functional programming, the developer of monads. He's worked on Haskell. He is one of the people who developed generics for Java, which many people use. He's here to talk to us today about faith, evolution, and programming languages. Philip Wadler, ladies and gentlemen.
It's a great pleasure to be speaking here. Thank you very much for inviting me. This is a variant of a talk that I first gave at UPSLA, and I think this is a good environment for it as well. So I spent a lot of my life trying to do what I call getting out of the functional programming ghetto. But for the purpose of this talk, I want to talk very much as a representative of the functional programming community, trying to address a much broader community. So the purpose of this talk is going to be to say a little bit about different kinds of programming languages and how they might relate and what functional programming might have to offer to the rest of the world. Now, so the title of this is Faith, Evolution, and Programming Languages. And faith and evolution have been together in the news. Some people see belief in evolution and faith as opposed. Many of us might take a different view and say, well, they're just two different worlds completely, right? I want my faith to know what to do when my mother dies and I need a ceremony, or when my children are born and I need a ceremony, and that has nothing to do with whether or not I believe in evolution. Some people think differently. My guess is that in this audience, the number of people who think differently and believe that faith and evolution are opposed, that if faith and evolution are opposed, it's evolution that has to go, that the number of such people would be small. In a contest between faith and evolution, evolution would win. But now let's look at the design of programming languages. And when it comes to how we go about designing our programming languages, or choosing our programming languages, in a contest between faith and science, I would say that more often faith wins. And one of the reasons for this may be one of the reasons that faith triumphed over science many thousands of years ago, which is that there wasn't much science around. And when it comes to the design of our programming languages, we don't have as much science as we might wish to draw upon. So that's my introductory spiel. And then part of this is multiculturalism. In Britain, this is very looked upon. You should support many different faiths. And often in the programming community, you will find people that support multiculturalism, that says, say, many different paradigms should go together. And then you find people who are more fundamentalist for whatever their brand of fundamentalism is. One particular divide that you find is that between static and dynamic typing. And I've actually illustrated this with Alonzo Church on the left and Haskell Curry on the right, because many years ago, before there were even programming languages, they were already having this debate, where Church said, you cannot talk about the semantics of a typed programming language unless you have the types, and Curry was saying, no, you can give it a semantics untyped and then layer the types on top later. So it's a very old debate. So I'm going to have 4 parts to this talk. It's actually quite a lot to cram in. So I will speak fast, but please do slow me down with questions if there are bits that you don't understand. I'm much more interested in communicating than in getting through it all. So I'm going to begin by talking about the origins of my own faith in functional programming, why I believe in functional programming and in types. And then I'll tell you a little bit about 2 pieces of work that I've done, type classes in Haskell and generics in Java. These, of course, were both very large projects, and I was one of the people who contributed to them. And then finally, I'll tell you about some work that I'm doing now. And I should mention, I said this was based on a talk I gave at UPSLA, but the last part of this actually came because after the UPSLA talk, I thought, you know, there should have been some relevant new work in there that fit with everything else. And after that, I did the work. So I'm going to tell you about that today. So where does my faith come from? Well, I'm going to tell you a story about two men. The first is Gerhard Gentzen. And I guess an interesting overlap with faith here is that I happen to be Jewish, and Gerhard Gentzen happened to be a stormtrooper. Now, so that leaves me at issue with him personally, but logically, his logic was impeccable. He made many remarkable contributions. So he introduced two, not one, but the two main systems of logic that we use today, one of which is natural deduction. So here it is from the original paper, written in 1935. And here it is the way that we use it now. And as you can see, they're identical, except that he wrote his letters in German. But apart from that, they look exactly the same. And his great insight was that logical rules should come in pairs. Introduction and elimination pairs. So here we have, on the assumption A, you can prove B, and that tells you that A implies B. And here we have, if you know that A implies B, and you know A, then you can conclude B, something which has been called modus ponens for about, well, somewhat more than 1,000 years. The actual principle is closer to 2,000 years old. And similarly, if you can prove A and you can prove B, then you've proved A and B. If you can prove A and B, then you can conclude A. So the reason these are in pairs is that this rule has A implies B in the conclusion. This has A implies B as one of the hypotheses, below the line, above the line. Similarly here, below the line, introduction rule, above the line, elimination rule. So here is a very roundabout proof of A and B from the assumptions B and A. So from B and A, I can prove B and A. And then here you've got a proof that B and A implies A and B. So I combine those and I get A and B. Of course, this is a very roundabout proof. I might want to simplify this proof. Gentzen was very interested in simplifying proofs because by showing you could simplify proofs, he could show that a proof only involved that thing and its subformulas. And then by knowing that a proof of a thing only involved that thing and its subformulas, he could show that there was no proof of false, giving a kind of consistency for his system. This was easy to do because false does not have many subformulas. It's sort of like, what part of no don't you understand? So it was very easy to show consistency of his system once he had shown that you could simplify proofs so that something only depended on subformulas. So here we have a formula, B and A implies A and B, which is not a subformula of the conclusion. So we would need to simplify to get rid of that. And in fact, we can simplify. And the important point to note here is that whenever you have an introduction rule next to an elimination rule, instead of introducing the thing and then eliminating it, you can just do things in a more direct style. So remember, the introduction rule said we will have some hypotheses of the form whatever it is to the left of the implies sign. So in this case, of the form B and A. And then over here, we're going to have some proof of B and A. So to simplify this, you just take this proof and copy it in place of each of the two occurrences of the assumption. Is there some pointer I could use to point directly at the screen? Let's see how well this works. Thank you very much. Oh, I hate these little tiny dots. Can people see that? OK. Oh, thank you, Neil. There we go. Oh, yes, good. Right, so now people have to be polite or else I can zap you. Right, so we take this assumption here and this assumption here, and we replace them by this proof here, giving this simplified thing. Now notice that simple here means we've gotten rid of this intermediate formula, but the simpler proof may actually be much bigger, because this could be very big, and we might be copying it many times. Nonetheless, in some sense, things are getting simpler. And notice that once we've done this simplification, this and I has moved on top of this and E. So we have and I followed by and E. So this says, well, if I know B and I know A, then I know B and A. And if I know B and A, I know A. Well, we could simplify that, of course, and just say, right, I know A. And now we've got a simplified proof that from assumptions A and B, you can conclude A and B. So in fact, you can do this with any proof, and you can always get rid of all the subformulas in the proof by following this technique. Part of knowing that this works is to show that this process must terminate. And that, in fact, follows, in this case, by simple inductive argument. OK, so that's what I wanted to tell you about Gerhard Gentzen. Now let me tell you about Alonzo Church, who was, among other things, the supervisor of Turing's PhD thesis. So many of you will have heard of lambda calculus, I expect. Hands up if you've heard of lambda calculus. Right, that is most of you, good. Hands up if you haven't heard of lambda calculus. I can use this on you, right. OK, and there it is, the world's first lambda. Not lambda is a Greek letter, but lambda is the binding of an abstraction operator. And we really like our lambdas, right? So for instance, here's a journal that I helped to found, which has lots of lambdas on the front. And that's a picture of the tie that I'm wearing right now. So Church wanted to use this as a meta-language for writing down logical formulae. And he originally did this in 1932 with an untyped lambda calculus. And it turned out that since you have fixed point operators, you could write down the equivalent of an infinitely long formula. And using this, using Curry's paradox, you could prove false, which makes your logic very powerful, but perhaps not very useful. So he needed to make his logic consistent, and to do this, he used the same trick that Bertrand Russell had first used to get rid of Russell's paradox, which was to introduce types. So in 1940, he wrote down his typed lambda calculus. And this says, for instance, that if x has type A, that's a free variable, and here's u, some term that contains the free variable x. If that has type B, then lambda x dot u is a function that takes an argument of type A and returns a result of type B. If S is a function from A to B, and T is a term of type A, then of course if you apply S to T, the result is a term of type B. If T has type A and U has type B, we can form the pair of a T and an A, which has type A and B. And if S is an A and B term, I can select the left component, which will have type A, similarly for the right. So here's a program. It says, here's a function that takes Z, which we can see up here is a pair of a B and an A. And what we do is we select the A from that, and we select the B from that, and we pair them up. So that means lambda Z, Z1, Z0, is a function that takes a BA pair and returns an AB pair. And here is a BA pair. So if I apply this function to this pair, I get an AB pair. So how would I execute this program? Well, what I'm going to do is I want to take YX here and substitute it for Z. So that gives me this program. And here's the thing showing that this program is well typed. And now I've got a YX pair from which I select the right component, and similarly the left component, and that simplifies down to this. So you may have noticed a slight similarity between what I showed you here and what I showed you in the previous thing involving Gentzen. Now, I told you that Gentzen did all this because he was interested in simplifying proofs, which is true. What I neglected to tell you is he didn't see it in that form. I mentioned he invented two well-known styles of proof, and the other, sequent calculus, he invented to show this simplification property. He did not manage to show it for natural deduction. But as you've seen, the way that you show for natural deduction is very simple. And Gentzen was a very clever guy, but in fact, he never saw it. He died at an early age. I feel like quoting Tom Lehrer. He once said, it's embarrassing to realize that when Gentzen was my age, he'd been dead for more than a decade. So Gentzen never saw this. A fellow named Pravitz finally saw it in 1965. Even though this style of simplification for type lambda calculus was already known in 1940 in Church's original paper. So the way I've shown it to you, the relationship between these things is completely obvious. How could you possibly miss it? But these two clever guys, Church and Gensen, did miss it. It wasn't until 1965 that Providence saw how to do the proof, and then not until 1969 that William Howard actually wrote out the exact correspondence I've just shown to you. And this was just circulated informally as mimeoed notes. It wasn't published until 1980. So 1935 to 1965 and then to 1980. Almost 50 years before you have published this obvious and in fact very, very important correspondence. And I think particularly for an internet company like Google where things go very fast, it's worth reminding people that sometimes ideas take a long time to come to fruition. As an academic, I always like to remind the funding agencies of that as well. So something very similar to what I showed you had been noticed by Haskell Curry. I've mentioned a few times before. So this correspondence that I've told you about is called the Curry-Howard correspondence. Nice double-barreled name because two people refined it in different forms. Now, the interesting thing about this double-barreled name is it predicts the existence of other double-barreled names. It says that when you have a nice programming language, there should be a nice logic that corresponds to it, and vice versa. Now, I showed you this just for one case, the simply typed lambda calculus, but in fact, this crops up again and again and again and again. It's a very robust correspondence. So, for instance, the logician Roger Hindley and the computer scientist Robin Milner both discovered independently what's now called the Hindley-Milner type system, which is the basis of the ML programming language and the Haskell programming language, among others. And the logician Jean-Yves Girard and the computer scientist John Reynolds both discovered what's sometimes called the polymorphic lambda calculus, or the Girard-Reynolds lambda calculus. And again, you will find that there's a logic and a programming language that correspond. And new ones are being discovered all the time. So for instance, Tim Griffin in 1990 worked out how, so you notice there was no law of the excluded middle here. Turns out that if you add the law of the excluded middle, that's equivalent to various other laws like Peirce's law. And in 1990, Tim Griffin published this nice paper saying, oh, look, Peirce's law is exactly the same as the type of call CC. And in fact, you can give it a semantics that's exactly like call CC. So you had this correspondence between classical logic and a programming language with continuation, such as scheme. And these sorts of things crop up all the time. In 2003, I managed to publish a paper giving a correspondence with sequent calculus. So it's a very deep correspondence, very robust. And the way I like to think about this is, say we managed to communicate with aliens in some time and we want to send them a program. Say we sent them a program written in Java. Right? You might have seen the film Independence Day. So in the film Independence Day, they kill the alien computer with a virus. And if you look at this virus in the moment it flashes up on the screen, it has lots of curly braces in it. At the time, I just moved to Bell Labs, and I thought, cool, I worked next to a guy, Ken Thompson, who's gotten his programming language into a popular film. This was back in 1996. Okay? It was before Java had spread through the known universe. So I figured this was C. But if you send C to aliens or Java to aliens, they might be able to decode it. But it's very unlikely that it's something that they would have discovered independently on their own.
Do you think we were intelligent?
That might be a problem as well. Okay. But now say that you sent them something in lambda calculus. If you sent them something in lambda calculus, well, they would probably already know natural deduction. And they must, therefore, have discovered lambda calculus if you just wait long enough, right? It took us 2,000 years to get from the Greeks discovering logic to get to lambda calculus, but we got there in the end. And I predict that if you talk to aliens, they would get there in the end too. So what I would like to say is that lambda calculus is the universal programming language. Now, I'd like to say that, but that would be wrong. It would be wrong because it is too limiting. Because imagine a different universe. In a different universe with, say, a different gravitational constant, I could imagine that. I could not imagine a universe in which modus ponens does not hold. I can't imagine a universe without the logics that we know. And therefore, I cannot imagine a universe without lambda calculus. So universal is the wrong name. It should be more general. There's this old question for a hard Oxford exam. Define universe. Give 3 examples. And it's a bit like that. So I've been trying to search for the right word. I've never come up with it. So if anybody could suggest the proper word, I'll pause here for a moment. I'd be very grateful to you. Maybe somebody will come up with it before the end of the talk.
Necessary.
Necessary.
In the modal sense.
Not quite the same ring as universal, is it? You need something at least as catchy as universal. Okay, that's what I was going to tell you about the basis for my faith and why I think that there is something really inherent and interesting about functional programming languages. So I'll just pause there for a moment to ask if somebody wants to ask a question about that part before I move on to a different part. Always a bad sign if you get no questions. Everybody saving them up for the end? All right.
I would add that when you get questions,
Will do. OK, so now let me tell you about a different piece of work. So this was done at the time we were creating the Haskell programming language, which to my surprise is 20 years ago. We are presenting a paper on it at the History of Programming Languages conference in June. And we had to deal with this problem of overloading. And we ended up by dealing with it by coming up with something called type classes. So there are places where you want to do overloading and places where you don't. I'd claim that Haskell does a pretty good job of capturing the kind of overloadings you want. So for instance, plus can be defined on int and float, but not on string. Right? Because defining plus on string is something very different. So here's an example of this where you want less than defined on many different types. So you want less than defined on int, and you want less than defined on characters. So here's the definition of less than on integers and characters, but we want to use the same symbol for both. So the way we do this is we say I have a type class called ord of A. And basically, ord of A holds whenever there's an operation less than whose type is take 2 A's and return a Boolean. And so int belongs to the type class ord, and char belongs to the type class ord. And now I can define a function max, which says if x is smaller than y, return y. Otherwise, return x. And using our good old Hindley-Milner type system, just slightly enhanced, we derive that the type of this is take 2 A's and return an A in the case that A belongs to the type class ord. A must belong to the type class ord because we've used this operation less than on 2 A's. That's only valid because A belongs to the type class ord. And I can say find the maximum of a list. So I'll take a list of A and return an A. If it's a list with just one thing in it, return it. If it's a list whose head is x and whose tail is xs, then find the maximum of xs and take the max of that with x. Since max has ord A in its type, maximum must have ord A constraining its type as well. And then, for instance, I can take the maximum of a list of integers or the maximum of a list of characters, which is written as a string in Haskell. Is that clear enough? Sort of nod your head, please, if that was clear. And ask a question if it wasn't. Now, the nice thing about this is we can give a translation. And the translation is very, very similar to what I showed you before. So remember that in what I showed you before, if you have an implication, it turns into a function. Of course, in Haskell, we already have functions. But if you look at this, it's a sort of implication. It says, if A belongs to the class ord, then Max has this type. So that implication also turns into a function when we want to implement these things. What we say is that we'll introduce a new data type, ord of A, which is just a record containing one field, less, which is a function that takes 2 A's and returns a bool. And so if you can, of course, have more than one operator in your type class, and then we'd have more than one field in this record. You have as many operators as you like. And now to say that int belongs to the class ord, what we do is we give an instance of this dictionary, where less is bound to the right function. Similarly for characters. And then when we define max, notice that this has now turned into an ordinary function argument. So we pass in this extra argument called D for dictionary. And then when we need to work out is x less than y, we extract the less than operator from the dictionary and then apply that to x and y. Similarly, we pass a dictionary into maximum, and when we want to call max, we pass that dictionary into max. And now I can call, so now when the translation of maximum applied to a list of integers takes an extra argument, which is inferred, which is this appropriate dictionary, and similarly for a list of characters. A way to think about this is that in object-oriented programming, if you called max, it would have two arguments, each of which is an integer, which points to the appropriate dictionary of operations on integers. And of course, this is often referred to, something like less than, is referred to as the binary method problem in object-oriented languages. Because in general, it can be difficult to make something object-oriented that varies in the behavior of two arguments rather than one. It can be hard to get that right in the object-oriented world. And that's because you have two different pointers to the dictionary here, and you need them to agree for this to be sensible. And there's not usually an easy way in the object-oriented world to be sure that these both agree. So the way to think of Haskell is it's just the same thing, but the dictionary's been detached from these things and passed in as an extra operator, which guarantees that you have just the one dictionary for both that matches. And then this extends to saying, let's say I've got orderings defined for a type A, then ordering can also be defined for the type list of A. So this would just be the lexical ordering. So here's lexical ordering defined in the usual way. And now this means that since less than is defined on characters, it's also defined on list of characters. Since less than is defined on integers, it's defined on list of integers. And since it's defined on list of integers, it's defined on list of integers, and so on ad infinitum if you choose. And the implementation of this is very similar. And basically, it just says we'll have a function that, given the implementation of ordering of less than on type A, gives you the implementation on type list of A. And then in order to compute maximum of a list of integers, we take this function and apply it to less than on integers, and then apply it again. OK, straightforward? Any questions about that? OK, so that's how it works in Haskell. And I'll tell you about a different piece of work I was involved in, which was defining generics for Java. So in fact, I've just finished writing, and there's my name in tiny print on the cover. But I've just finished with a colleague writing a book describing how generics work in Java. Very well reviewed, I'm pleased to say. So you're all probably familiar by now with the problem that generics solve, but just to motivate this briefly, how would you represent an integer list in Java before there were generics? Well, that's easy. You'd give it the type list. Let's say I had a list of strings instead. What type would I give that? Oh, that's easy. It's a list. And if I had a list of strings, that's also easy. It's a list. So that's nice and simple. But possibly it's too simple. And what we'd really like to do is this, and write out specifically, declare in the type that this is in fact a list of string. And so generics in Java let you do that. And there are, of course, two important relationships with C++ to be noted here. The first is syntax. We have exactly the same syntax. And the second is semantics. We have a completely different semantics. In particular, we have a semantics. So here's how this works. And the design of generics in Java is based upon this principle called erasure. And the motivation behind erasure is evolution. In this case, the evolution from legacy code to generic code. The reason that it's done with erasure is to promote evolution. So here's the classic example. Here's a stack implemented in terms of lists. Push, just add something to the list, and pop, remove something from the list. And of course, the way you would define something in Java before generics is just as all the elements of the list would have type object. If you want to have a stack that could be a stack of any type, you would say that the elements were objects. So when you push, you'd push an object. When you pop, you'd pop an object. Here we have object appearing in the middle of the code. And then if I wanted to build, say, a stack of integers, then I'd just say have a new stack. When I push, I'd put an integer in there. And then when I pop, I would have to cast back to integer, of course. So I've always thought that the object was well named because object always shows up in your code when, because you don't have generics, you'd have to say object is the type of your element. So I thought it was well named. When you see it, you should object. So what you would want to do, of course, is say I have a stack of E, and that's implemented as a list of E. And when I push something, I push an element of type E. And when I pop, I get out an E. And now when I declare a stack, I say it's a stack of integer. And I can just push 42 on it. And most importantly, when I pop, I do not need to cast. That cast is inserted for me automatically by the compiler. Now, I mentioned that generics are implemented by erasure. And what that means is that the implementation of this, where I say stack of E, is to erase that of E and implement it this way. And that means that when I pop something off the stack, that's actually implemented by inserting into the compiled code the necessary cast. The reason that is important is it says if you write the code in legacy form, or if you write the code in generic form, you get exactly the same bytecode. And that means we can mix and match. So in particular, it works perfectly well. Whoops. It works perfectly well to use, wait, am I missing one? Yes. It works perfectly well to have a generic library, but a legacy client. And indeed, this was very, very important. When generics were first introduced in Java, it meant for things like the collection library, which I know is dear and dear to Josh's heart, that you could genericize the whole thing, and it would not break any existing clients. So that was really the killer argument for implementing generics in this way. You're smiling. Is there something?
It didn't break the existing ones, but new ones.
I don't like that.
Yep, well, I'll get into that. And also, it means that you could go the other way around and genericize. See where it says legacy library with generic client? There are two small spelling errors there that should read generic library with legacy client. So if you have the source of your library and you want to update it, no, wait a minute. I'm confused. Generic library with legacy client, correct. Legacy library with generic client, sorry, this is correct, sorry. So here we've genericized our client, right? It's got stack of integer. Here we've got an old library that we want to make minimal changes to. We've got the source, and what we do is we just change the declarations here, but notice I've left the code alone. Of course, here the code is one line, who cares? But if the code was hundreds of lines, it might be important to you that you just change the type signatures and nothing else. And then when I'm done, I have to cast it. And of course, it can't check that this cast is correct, so it gives you a warning when it compiles the code. But in this way, you can now use the code from here, and it will type check that everything works out properly, as long as you've assigned the correct types here. But that only works if you have the source code. But even if you don't have the source code, you can do this. You just write the new signatures. You give completely empty bodies. You write the client as you want. You compile the client against these signatures. So you compile the client against the newly genericized code. But then when you run it against the legacy code. So you can update even if you don't have the source for the library. OK, so that's the good news. And that's why we did it this way. And both Neil and Josh, who are well aware of the limitations, know that although this works very well, there are other aspects that don't work well. In particular, trying to create a new array doesn't work well because we've erased all the type information. But because of the way that arrays work in Java, in order to make them type safe, you need the type information to check. So creating new arrays is a bit tricky, and you have to pass around some token or existing array with the type information to make that work well. And again, please buy my book, because it explains it in great detail how to do that right, and how not to violate things like the principle of truth in advertising.
How many copies should we buy?
Lots. Okay. Now, I told you a bit about type classes in Haskell, and in fact, you find exactly the same idea now cropping up in Java. So I mentioned that binary methods are difficult, but in fact, with a little trick that was learned by looking at type classes, binary methods become easy. You just add a little type parameter, and when you want to compare things, so this says a type belongs to comparable of t if you know how to compare it to a t. And then you declare integer as belonging to comparable of integer, and character as belonging to string as belonging to comparable of string, and so on. But num, for instance, you cannot compare to arbitrary numbers, so num does not belong to comparable of number. So you can make this be a compile time error, but both of these work out fine. And then if you want to find the maximum of list, that's again very easy. The only tricky bit is in the type, where you say, okay, maximum takes a list of t and returns a t for any t such that t extends comparable of t. So this is the equivalent to, in Haskell, saying ord of t with the double arrow. And many people, when they first see this idiom, are mystified by it, but that's where it comes from. And then I mentioned that this would extend to list of lists and so on. And so in Haskell, we implicitly would create an operator that, given less than on type A, would give you less than on type list of A. Here it's written out explicitly in Java, so something that takes an implementation of less than on type E and gives you an implementation of type less than on list of E, written using lexical comparison. And then if you want to compare list of E's, you just apply it twice, as before. And you remember I gave you this nice example of forming a list of integers and finding the maximum of the list of integers using this implicitly created dictionary. Right? That's the translated code. Right? Here's the original Haskell code, just this one line. And it's very, very easy to do the same thing in Java. Let me just show you what it looks like in Java. Very simple and easy. There it is. Just slightly more verbose. OK, so that's what I want to say about Haskell and Java, and how some ideas from Haskell escaped into Java, where real people would use them. Any questions? Yes, please.
Is there a reason we don't have type defs in Java?
Is there a reason that we don't have type defs in Java? Gil Bracha, who was in charge of it, just said he wanted to keep things as simple as possible. I, in fact, argued in favor of type defs. OK, so let me go on now and tell you about some new work that I've done, which, of course, I'm very excited about because it's new work. And this is drawn from these 3 pieces of work. And basically, looking at them, I saw that there's a common theme running through all 3. So the same ideas. These have all been done in the last 5 years or so. So here's the idea. I mentioned evolution. I'm going to return to that theme. And I also mentioned multiculturalism. And the notion here is you have some dynamically typed languages, like, say, Smalltalk or Python or Ruby. And you have statically typed languages, like Java. And the question is, could you make the 2 play together in a friendly way? And we already saw this sort of thing cropping up with using erasure to define generics in Java, so that you could have the old legacy type list, which in fact was untyped or dynamically typed with regard to the element type of the list, and the new type list of E. So again, you had typed and untyped playing well together. Could we do the same thing for a language, say, such as Scheme and Haskell, get them to play well together, Scheme being dynamically typed and Haskell being statically typed? So here is a untyped version of a simple program to indicate that it's untyped, since, of course, I'm a typed kind of guy, so I'm going to make untyped be the exceptional case. So it indicates exceptional, I write these little brackets around it. So this is an untyped program. And just say x is 2, f is the increment function, and h is higher order. It takes the function g and applies it twice to x. So h of f, if f is the increment function and x is 2, is of course going to be 4. And here's the same thing typed. Now, thanks to Hindley-Milner type inference, we don't in fact need to write out lambda y of type int. This could be inferred for us. And similarly, it would infer that g is a function from integers to integers. But just to keep things nice and simple, I'll use simply typed lambda calculus and write out all my types. But in practice, we'd want to use Hindley-Milner. So here's the same program typed. Now, evolution would mean we'd want to mix and match the two and have some bit that's typed and some bit that's untyped living together. So for instance, here's some legacy code to do increment. And here's some modern code to bind x to 2 and then to h, which takes an int to int function and applies it twice. And of course, this will evaluate to 4 again. And then the question is, how do we make sure that this is type safe and reports an error in the proper way if something goes wrong? And notice these little superscripts p and n. I'll say more about those shortly. And then here's another example of a program. Oh, sorry. This is the same program. But I've changed one bit of it. Instead of this being the increment function, it's the constant b function. So no matter what it takes, it would return the character b. Now, in this case, things will go wrong, because if we try to apply g to x here, we're not going to get out an integer like we're supposed to do. We'll get out a character. So something goes wrong, and the something that went wrong is with this function here. And these labels here tell you who to blame if things go wrong. So this idea comes from Contracts by Findler and Verleisen. And the important thing is that there are two places you might blame. If things go wrong, it's either with the term in here or with the environment. So this is an example where what's wrong is with the term in here. It's not returning an integer like it's supposed to do. It's returning a character. So what went wrong here is with this term. It's not, in fact, of type integer to integer. Now let's look at this example the other way around. So here I have some untyped code with some typed code buried inside it. And now this is the increment function. And I pass it into here. And so again, this returns 4, as you'd expect. If I changed it so that x, instead of being an integer, is a character, something will go wrong. Now, what's gone wrong? Casting an integer into an integer to a dynamic. This is an integer to integer. You can't fault this. This is perfectly right. What you have to fault is the environment, which has passed in a character rather than an integer. So in this case, the fault belongs to the environment, and we say blame n. So these are called positive and negative blame. Positive means it's the fault of the thing in here. Negative means it's the fault of the context, of the environment. Now, I've talked about untyped programs, but what I mean by untyped is unityped. We just add a little I in there. This is a slogan due to Bob Harper. And the notion is everything has the same type, which you've already seen written down a few times, din. Robbie Findler had another nice paper where he actually wrote out the type rules for scheme, and everywhere in these type rules you see TST. Then you read the paper carefully and you discover TST stands for the scheme type. Right? There's just the one. So I'm calling that din, short for dynamic. So in fact, when I write these untyped programs with brackets around it, it just means inserting all the necessary coercions. So if I have a lambda expression here, it's going to take an argument that's dynamic, and then the expression within it will, of course, be dynamic. So I need to cast a dynamic to dynamic function to a dynamic. Similarly, to apply, you take this dynamic, cast it to a function, and then apply it to the argument. So just adding these casts is all we need, and that's all that these brackets mean. It's adding in the suitable casts. Right, and then If I cast an integer to a dynamic and then back again, that works fine. If I cast an integer to dynamic and try to cast it back to some other type, that does not work fine, and it raises blame. That's always going to be positive blame, because it's this thing in here that was wrong. This is not a character. It's its fault. All right, so where does negative blame come from? It comes from functions. And this is the key trick. This is the contract trick due to Findler and Felizen. So let's say I've got a function from dynamic to dynamic. I cast it to a function from integer to integer. So here's the function. Take a dynamic y, add 1 to it, untyped, to give a dynamic, and then apply that to 2. OK, so what we do is we break this cast into 2 smaller casts, one on the argument, which will cast it from integer to dynamic, and one on the result, which casts the result, which is dynamic, back to an integer. So 2 goes to the untyped 2. You add 1 to it to get an untyped 3, and we cast that back to a type 3. So notice that the particular cast we're doing here is narrowing. These are wide types, right? Dynamics very general, integers a narrow type. So we're making the type much more specific. Note that when you do that, this cast here must always succeed. But this cast could fail. Right? An example is, whoops. Missing example. All right. If this had been the constant b function, then when we tried to cast that to an integer, it would fail. Oh, dear. Help!
The laptop still seems to be okay from your point of view.
Much better. OK, so notice that this cast here must always succeed. Oh, notice also that when we do this reversal, right, here it's din to int, but here it goes the other way around, int to din. So when we reverse, notice that the negative and positive trade places. So here's an example going the other way where we're making things wider. Int to int goes to din to din. And again, we just break it up both ways. Again, we reverse it here. So now we'd convert din dynamic to integer, add 1, and then convert the integer back to dynamic. Now, whoops. Oh, both examples are missing. Interesting. OK. We could replace this, say, by a character instead, right? It still has, if that was bracket character A bracket, that'd be an untyped in. So you could do it. It'd be well typed. But now if we try to coerce the letter A to an integer, this will fail, and we will get negative blame. So if you're widening, you can get negative blame, but you would never get positive blame, because integer to dynamic will always succeed. So just to review, if you're narrowing things, that can never give rise to negative blame, but could give rise to positive blame. If you're widening, it can give rise to negative blame, but can never give rise to positive blame. Yes?
Why do you call the kinds of blame negative and positive?
It corresponds to positive and negative positions in covariance and contravariance. Thank you for the question. Let's see, is there anything else I want to say about that? Right. OK. A related issue here is contracts. So this is the idea that occurs in again, in the original work of Findler and Felizen, and this particular type system is due to Cormac Flanagan. But the idea is now I declare a type nat and say nat is all integers that are greater than or equal to 0. And I have coercions like int to int goes to nat to nat. So this is before I talked about an untyped world and a typed world. Here I have a typed world and a very strongly typed world. And one reason that I'm interested in bringing together the typed and untyped worlds is because I'm also very interested in bringing together a typed world with a very strongly typed world, where the types are really telling me a lot. Now, in general, I might not always be able to prove that something is a NAT. So in general, I might have to test at runtime. But nonetheless, I could get a lot of value out of such a type system. Notice that we do a dynamic test here that 2 is really greater than 0. And here, we'll test the argument and then test the result. But notice that here, it's statically typed. We're guaranteed that if X is a NAT and G takes NAT to NATs, the result will be a NAT. No dynamic test needed here at all. The static type system is proving a great deal for us, even though we have no theorem prover or anything here. So I think this could be very useful.
So hang on a second. The second line with the
Assignment
assignment.
to F. If the function was y minus 1, where does the failure happen?
It will happen at runtime, and it will be, this will break up into a contract check on the argument and a contract check on the result. The contract check on the result will fail.
So that's a partial function.
Yes.
If you could repeat the question.
Sorry, the question was, could you repeat the question?
Yeah, if it was y minus 1.
If it was y minus 1, where would things go wrong? And the answer is that checking the contract that int can be converted to a NAT would fail on the result. So the way to understand this is in terms of subtyping. So the normal notion of subtyping has this contravariant rule. A function from S to t is smaller than a function from S prime to t prime if S prime is smaller than S and t is smaller than t prime. So you have this sort of inversion going on, very much like the flipping of the blame that I showed you. This is sort of where it comes from. Now, if S is really a subtype of T by these rules, so for set types, it would mean that the condition S on this set implies the condition T on this set. And notice, very importantly, that for dynamic, the only thing that dynamic is a subtype of is dynamic. This is surprising. In Cormac Flanagan's original formulation, it looked exactly like this, except he had any type is smaller than dynamic, which is what you might expect. But if you do, blame will go wrong. He was lacking the notion of blame. Blame is very important, right? And it's important in a software engineering sense, right? I've showed these cast on individual tiny functions that are one line. But the point is, if you have several large modules written by different people, one typed and one untyped, where does the blame go? So if something is truly a proper subtype, then the answer is that this cast will always succeed, and it will never result in any blame, positive or negative. Now, the technical contribution of the work that I'm showing you is that we can break that subtyping down into 2 parts. Positive subtyping, which only looks at the covariant or positive positions in the type. That is everything that is to the left of an even number of arrows. And negative, which are things to the left of an odd number of arrows. So what we do is we break it down into positive and negative. Again, we have this flipping of things, but notice that in the argument position, the contravariant position, we now use the negative subtyping instead. So, and then this is just as you'd expect. And notice that now, positively, anything is a subtype of dynamic. And the other way around, negatively, anything is a subtype. Oh, that should be a subtype minus there, missing minus. And notice that there's no condition that we check here at all. In the argument positions, we just won't bother to check this subtyping. And this ends up giving you a definition where something is a negative subtype if you take a broad concept and give a more precise concept. You have a broad concept and a more precise concept. So the cast here, going from broad to more precise, is a narrowing. And remember, narrowing never casts negative blame. Widening never casts positive blame. So what does this tell us? It says if we've mixed typed and untyped programs, here's an example of such a mix. It's a positive subtype, so it never casts positive blame. So when we go from dynamic to the typed world, the fault, got this the right way around? The theorem gives us that the fault is always inside here. And the other way around never casts, right, it can cast, and here, the other way around, right, dynamic, we're getting narrower, never casts negative blame. So notice here, right, when we went from dynamic to int, if we pass something in other, oh, that's right. This is going from int to dynamic, which would let us pass in something like a character, which could cast negative blame. This is precisely why negatively it's OK for any type to be a subtype of dynamic, but not positively. And why you need, if you have both negative and positive, then you never cast any blame at all, and it's like this. So the important thing to learn here is, OK, in this case, if we're going into the dynamic world, into the untyped world, then it can cast negative blame, but it won't cast positive blame. So the fault always belongs negatively, outside. If we cast into the dynamic world, the fault belongs in the dynamic world. Here, if we have a negative subtype, we're casting from the dynamic world out to the typed world. Any fault that happens must be positive. It can't be negative, so it belongs in here, in the untyped world. So this theorem proves for us just what you'd expect, that if things go wrong, it's not in the type-checked bit, it's in the untype-checked bit. And furthermore, this generalizes to tell us if something goes wrong, it's not in the more specifically typed bit, where we know these things are naturals, it's in the less typed bit. So this gives us a new slogan for type safety. Right? Milner's slogan was that well-typed programs can't go wrong. Harper and also Felizen and Wright gave us a different way of proving this theorem, which said well-typed programs don't get stuck. And you today have seen yet another way of doing this, which gives us the slogan, well-typed programs can't be blamed. And I'll finish up there. Thank you very much.
Wasn't links something to do with compiling Haskell into JavaScript a couple of years ago?
It was indeed. What I ran out of time to show you about is links.
Repeat the question.
Oh, right. So the question was about what is links, basically. I'd mentioned links in these slide titles, but I didn't show it to you in the talk because I ran out of time. But links is something that we're working on, which is about the following idea, right? You all know about three-tier applications, and you'll have your server code written in Java or Python, perhaps, and then your browser will have JavaScript in it, and your database will have SQL or perhaps XQuery. And what we do in links is we write everything in links, and we compile to JavaScript for the browser and compile into SQL for the database. So this bit's very similar to what GWT does, but we're trying to do more, so we actually have it the case that the server can make calls to the browser and back the other way. And in particular, we take charge of everything that you need so that when something is in the browser, it doesn't need to be on the server. All the parameters you need are stored in the browser and sent back to the server. So this common style of doing things like in Seaside, where it says store closures on the server, we don't need to do that. We put all the information out into the browser and send it back to the server when we need it. So you can bookmark your pages, and you never clutter up the server. And we have that all running now. Yes?
Are you familiar with the work by Andrew Longstain's group at Indiana University on concepts? And if so, do you think they've just reinvented Haskell type classes, or do you think that there are any important differences?
OK, the question was about concepts, which are an idea for C++, and whether they're just reinventing Haskell type classes. And the answer is yes, they are, and they know they are. They cite the type class work. So this is, looks like, to me, hopefully another chance for ideas from Haskell to get out into languages used by a different group of people. So yes, tell everybody loud and wide, yes, concepts are good, and yes, they are type classes from Haskell. Yes?
the fact that you're developing a new language and the compiler for that language, as I saw, is in OCaml. Does that mean that you're losing faith in Haskell?
Ah, right. So, in fact, Lynx is implemented in OCaml rather than in Haskell. That was really largely a matter of wanting to learn something new. And also, it was because we felt that there would be places where we would need side effects, such as writing to the database. And so OCaml seemed a better match. And mainly, I did it to learn more about OCaml. And having done it, I'm now happy to do future work in Haskell. But OCaml is still a very impressive language. I would not run it down at all. Yes?
So, speaking in the Java language, you can generify a class of a type, or maybe 2 or 3. Is there any idea of actually being able to generify on a variant number of types?
OK, so the question is, when you generify a class, you could have 1 type parameter, or 2 type parameters, or 3. Could you generify over a variant number of type parameters? And that's not supported. And even trying to think of such a thing makes my brain hurt. I know very few languages where you can do that and where it's useful. Do you have an example where you want to do that sort of thing?
I kind of needed that, and I've worked around not having it.
Wow.
Typing tuples or functions within the type system.
Oh. Right. Well, of course, the real solution to that is to have tuples or functions in the type system.
This would allow you to describe them in the same generic way.
No. It's the other way around, right? Tuples come from and. Functions come from implies. Those are really basic. That is my faith.
So it is, in fact, easy to emulate that, this pattern that we call a type safe heterogeneous container pattern. And I can send you slides for that later.
OK, so maybe there could be a nice discussion offline, which I'd like to be involved in about this to learn how that works. But let me answer your question in a different way. You're saying, well, I had this type system here. If I was untyped, it'd be easy to do all this, right, and have general tuples and, or general functions. But since I'm typed, it's harder. This is precisely why I want to put the typed and untyped worlds together. So you could do that in an untyped way and then cast it to be typed everywhere outside the core implementation. So that's why I'm interested in bringing these 2 worlds together. And a further answer to your question, I see now, because you've come up with some good examples, I was being a bit too facetious saying, why would you ever want to do this? There are dependently typed systems that would let you get at this sort of thing. And maybe in the offline discussion, I could say a bit about that. Thank you for the question. Yes?
That's where I was going to go was, do you think this kind of coercions with positive and negative blame can extend to dependent type systems?
Yes.
Where we can mix dependent and non-dependent worlds?
Yes.
Cool.
There's already been some work by Walker and others. And that's what I'm going at. And in fact, I'm looking now at doing the same sort of thing for polymorphism, which looks like a lot of fun.
Can effects and constraints be usefully integrated into a type system?
Can effect constraints be usefully integrated into a type system? Probably. No, absolutely, because that's exactly what we do with monads in Haskell. So monads capture notions of side effect, and you can use the type class system that I've shown you here, a nice generalization of it due to Mark Jones, to capture generalizing over an arbitrary monad, which essentially captures generalizing over effects. So I could tell you more about that offline if you were interested. Yes?
Are you going to cast dynamic results to monads? So would you fault if you didn't cast the IO monad and the dynamic function did something to the outside world?
OK, so I just said the word monad. I hope people don't all run screaming from the room. And the question was?
So for example, if I tried to cast printf, which returns the number of characters printed to an int, would it freak out because it should be an IO int?
It depends on how you handle side effects. So in Lynx, in fact, we just have side effects. Okay. We're planning on, in fact, as this other person suggested, adding a effectful type system that captures what side effects occur. But essentially, you'd need to have the right type. So if your type system involved effects, you'd have to have the appropriate effect type in there. Yes.
So that system is about bringing together non-typed and typed systems. But in large software systems, often I see that there are like many typed systems trying to talk to each other. And this is fine if we have like the same version of software and the same protocol all around. But sometimes we need some slack. So strong typing may be a problem there, so to say.
Right, so the question was, well, you're talking about bringing together typed and untyped. In fact, let me be more specific about that. What I'm talking about bringing together is less typed and more typed, or vice versa, of course. So that the contracts, for instance, something like natural is getting very precisely typed, and that's what's interesting me. But you're talking about, well, what if they're differently typed? Which is also a good question, and I don't really know the answer to that one. That partly comes out of my faith again, where I'm particularly interested in the type systems that arise from natural deduction. And so that's a particular type system that I think is the right one. But in fact, in reality, you do get lots of other type systems. And how to integrate them is an interesting question, but not one that I would claim to have addressed yet, except to the extent that maybe if you factor it by going through a completely untyped system, that might be useful. Well, thank you for your attention and your questions. Oh, I forgot to tell you one last thing. Sorry about this. But it is very important that you know, right, when you bump into a hard problem, you should think, this is a job, or lambda calculus. Thanks very much again.